This video is going to cover section 3.5 on tree and Venn diagrams. So a tree diagram is a special type of graph that we can use to help determine the outcomes of an experiment. It consists of branches that are labeled either with outcomes or frequencies or probabilities. Tree diagrams can make some problems easier to visualize and solve. So again, it's that idea of if we write out our sample space, if we can see everything in front of us, it's easier to figure out what we're being asked and how to answer that question. So an example is that a family wants to get each of their 3 children a pet, either a dog or a cat. And in how many ways can this be done? So a tree diagram can help to write this out and sort of sort it. So the first child can choose a dog or a cat. The second child can choose a dog or a cat. Now, if the first child already picked the dog, here we are along this branch. If the first child picked a cat, we're here along this side of the branch. So as each child picks their pet, we have these different outcomes. So down here on the bottom, we have our full sample space. And if we go down the branch vertically, we can see all the different possibilities for this family. So there's 8 ways that this can be done. We can have dog, 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 cat, dog, cat, dog, dog, cat, 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 dog, dog, cat, dog, cat, 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 dog, and cat, cat, cat. So those are represented here with all the letters. So here we have it listed out, our sample space, so we can see it from the tree diagram as well. And what's the probability the family will end up with all dogs, or that they will end up with exactly 2 dogs, or at least 1 dog? So this problem is also getting into all the different types of wording that we see with these types of probability questions. So the answer for if ending up with all dogs, so 3 dogs. So if we look here at the sample space listed out, or if we look in our tree diagram, we see there's only 1 possibility out of the 8 where we end up with dog, dog, dog. So 1/8 or 0.125. Exactly 2 dogs, that could be dog, dog, cat, dog, or cat, dog, dog. So there's 3 possibilities out of 8, so 0.375. And then at least 1 dog, so that could be 1 dog, 2 dogs, or 3 dogs. So we can have at least 1 dog. It's this one, 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 not this one. So you can either add these up and see that there's 7 options out of 8 here, or you can realize that it's the complement of all cats. So you could say 1 minus 1/8. That's also going to give you 7/8, which is 0.875. So different ways that you can think about these problems. So here's another way to do a tree diagram. So in a standard deck, there are 52 cards. 12 cards are face cards. That's our event F. And 40 cards are not face cards. That's our event N. We're going to pick 2 cards, one at a time, with replacement. So that means we put the card back in after we pick it. All the possible outcomes are shown in the tree diagram as frequencies. And then we are going to use the tree diagram to calculate the probability that we get a face card on our first pick and a face card on our second pick. So FF. So this time, instead of doing like dog, cat, or face, 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 because we need 12 branches and then 40 for the not face cards, we're saying right here in this number, this frequency, how many ways we can pick that. So there's 12 ways to pick a face card. On our second choice or pick, our draw, there's also 12 ways to pick a face card. There's also 40 ways to pick a non-face card. We picked non-face card first. There were 40 ways to do that. Then there could be 12 face card ways and 40 non-face card ways. So to get these numbers down here, where this is face-face, we multiply going down along the branches. So 12 times 12 is 144. 12 times 40 is 480, and so on. So as I said, you multiply going down the branches to get the frequencies for each option. And then the total number of outcomes to figure out how many outcomes are in our sample space, you add up going along the bottom of our tree diagram. So 144 plus 480 plus 480 plus 1600 gives us 2,704 total outcomes in our sample space. To figure out the probability that we did a face card and then a face card, we go down that branch, face card, face card. There's 144 outcomes in that event. So 144 over 2,704 gives us 9 over 169, or 0.0533. So it's not straightforward where you can just necessarily read it off. You have to do a little bit of work to find out your total in your sample space. But once you have it listed out, it's pretty easy to figure out the answers to these questions. So this is similar, but this time we have the probabilities going down along the branches. So 12 over 52 instead of just the number 12. But this problem we're not replacing. So this is without replacement. So as you go down and you pick a face card, 12 out of 52 is the probability. Picking another face card, well, you didn't put the first one back. So now there's only 11 possibilities out of 51. Notice how both the numerator and denominator changed. And so then to get the final number or probability down here, same as before, multiply going down the branches. So 11 times 12 is 132. 51 times 52 is 2,652. Same thing going this way. Again, notice how the denominators change and then the numerators depending on which card you pick. So this little thing here just says the probabilities are listed along these branches, and notice how the denominators and some of the numerators change due to the without the placement condition. So let's figure out the probability, and I'm going to jump to the next slide, that we picked a face card, then not a face card, or not a face card, then a face card. Find the probability we picked not a face card given our first pick was a face card. Find the probability that we picked at most one face card. So that's one face card or no face cards, but not two face cards. And the probability of at least one face card. So FN or NF. So we go down here. Here's FN and NF. So these are independent. So when we do the or, we can just add them together, the addition principle. There's no, or I guess they're mutually exclusive. There's nothing that overlaps that we have to worry about subtracting. So this is just the 480 plus 480 over the same numerator. We get 960 over 2,652, or 0.63620. What's the probability we pick a face card given our first pick, not a face card given our first pick was a face card? So go down the face card branch first and then down the not a face card. So this is our second draw. We've already picked our face card. So it's going to be 40 over 51. So that one's kind of nice because you can just look right on the diagram and get your number out, your probability. The probability that you pick at most one face card, so not this one. So we could do, 1 minus that probability, or we can add up these three probabilities, which I think is what I did here. 480 plus 480 plus 1,560. So that gives us 2,520 divided by 2,652, or 0.9502. What's the probability we pick at least one face card? So one or two face cards. So we're going to add these three up, or we're going to say 1 minus the no face card event. And we get 0.4118. Here's the addition, the sum, and then our decimal probability. So try it, 3.26 from our book. Suppose there are 4 red balls and 3 yellow balls in a box. 2 balls are drawn from the box without replacement. What is the probability that 1 ball of each coloring is selected? So we can see that there are 7 balls in total, We're going to do a tree diagram, and we're going to label each branch with the probabilities for each pick. So here we have our tree diagram. Pick a red, so that's 4 out of 7, or a yellow, 3 out of 7. We're not replacing, so then our next pick, red, we're going to change the numerator. Now there's only 3 red balls to pick from out of 6 total, because we've already picked one out. But if we pick yellow, there's still the 3 yellow, but we still only have out of 6 because we already picked one ball. And then we go down, we multiply going down the branches to get those final probabilities. So red is 12 out of 42. Red yellow is 12 out of 42. Yellow red is 12 out of 42. And then yellow is 6 out of 42. So to get one ball of each color, yellow red or red yellow, add those 2 probabilities up to get 24 out of 42, or 4 over 7, or 0.5714. So our next idea is the Venn diagram. So a Venn diagram is a picture that represents the outcome of an experiment, and it generally consists of a box that represents our sample space S, together with circles or ovals that represent our events. So if the events share outcomes in common, those ovals or circles will overlap. If they don't have any in common, they won't overlap. We're going to see mostly examples where they do have something in common. So suppose an experiment has the outcomes, the numbers 1 through 12, where each outcome has an equal chance of occurring. Event A is going to be the outcomes 1 through 6, and event B is the outcomes 6, 7, 8, and 9. So it's when you are going to draw your Venn diagram, figure out your and, what they have in common first, because then you can draw that overlap and figure everything else out. And the or are the numbers 1 through 9. So the Venn diagram for this situation looks like this. We have the rectangle that represents our sample space S. Event A are the numbers 1, 2, 3, 4, 5, 6. B is 6, 7, 8, 9. And 6 lives in the overlap of the 2 ovals. So knowing the and helps you lay everything out in your Venn diagram, because you put the and part in first and then fill everything else out. You don't want to include 6 over here because you don't want it to count twice. Same thing, you're not going to put it over here. It has to live in both because it does. And then over here we have 10, 11, 12 because they're in our sample space, but they're not in event A or in event B. So they sort of live separately over here. So suppose an experiment has the outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal a chance of occurring. We're going to let event C be the colors green, blue, purple. P is going to be red, yellow, blue. So then C and P, what do they have in common? They have the color blue. C or P are the colors green, blue, purple, red, and yellow. Again, don't repeat blue because it's in both. You only want to list it once. So a Venn diagram that represents this situation, I always like to put my and in first and see I have labeled each event. C are these colors, P are these colors. Blue is in the overlap because it's in the and. And then the colors that are not in either event C or P live outside of the circles, but still inside of the box that represents our sample space. So a lot of examples showing these kind of ideas, but each one, I think I'm trying to show you something a little bit different. So we're going to roll a fair 6-sided die. Let A equal a prime number of dots is rolled, and event B is an odd number of dots is rolled. So the sample space for rolling a fair die are the numbers 1 through 6. Event A is going to be 2, 3, and 5. Those are the prime numbers in this sample space. And then B is 1, 3, and 5, the odd numbers in this sample space. So again, look for the and, 3 and 5. And then I write down the or, just to have it out there. And then a Venn diagram showing this situation looks like this. So again, 3 and 5 are in the and, the overlap. This circle represents all of A, 2, 3, 5. This circle represents all of B, 135. We're not repeating any numbers. We're not putting something in a different section when it belongs in the overlap or doesn't. And then here are 4 and 6, which are not in A, nor are they in B, but they are in our sample space, so they're going to be in that box. So here we have percents instead of numbers or events or outcomes, I mean. So 50% of the workers at a factory work a second job. 25% have a spouse who also works. 5% work a second job and have a spouse who also works. So draw a Venn diagram showing these relationships. So we always want to figure out, so like if this says, this is percentages, we want to put them in the proper part of the Venn diagram. Start with the and work your way out. And you have to subtract so you don't count people twice. So you want to think about what's in the and, what's in both of your events. So we have the event work a second job and the event spouse who also works. So this 5% is the and, works a second job and has a spouse who also works. That's going to go in our overlap. So our Venn diagram is going to start out looking like this. Here is the event that people work a second job. Here is the event that they have a spouse who works. The overlap is for the both, that they have a second job and a spouse who also works. Notice that 45 plus 5 adds up to the 50% of factory workers who work a second job, and the 5 and the 20 add up to the 25% who have a spouse who also works. So I took the 5 out of the 50 to get this 45. I took the 5 out of the 25 to get this 20. That's so we don't count the people twice. In a bookstore, the probability that a customer buys a novel, I can't move my face, here we go, is 0.6, and the probability that a customer buys a nonfiction book is 0.4. Suppose that the probability that the customer buys both is 0.2. We're going to draw the Venn diagram. We're going to find the probability that the customer buys either a novel or a nonfiction book. We're going to describe the overlapping area using a complete sentence. And then we're going to answer the question, suppose that some customers buy only compact discs. We're going to represent that in our Venn diagram with a new oval. So here's our original Venn diagram. Buy a novel. So we know that it's, so here's our and, right? Because they tell us that buys both a novel and a nonfiction book is 0.2. So that goes in the center. Buying a novel was 0.6. So 0.6 minus 0.2 gives us the 0.4. Buying a nonfiction book was 0.4. So 0.4 minus the overlap, the 0.2 gives us 0.2. So this is the buys a nonfiction book only, buys a novel only. So that's something to think about as well. So there's the and, they buys both, and then there's the buys only one or the other. So what's the probability that the customer buys either a novel or a nonfiction book? So you can think about just adding up the numbers across, 0.4 plus 0.2 plus 0.2, that gives us this first line here, which is 0.8. Or if you think back to the addition rule, so buying a novel was well, I think I did this the other way. So this is nonfiction was 0.4 plus buying a novel was 0.6 minus novel and nonfiction, and we still get the 0.8. So you can do it either way. You can add these up going across, or you can look back to your original problem and say 0.6 plus 0.4 minus 0.2. So how can we describe this overlapping area with a complete sentence? This overlapping area represents people who buy a novel and a nonfiction book. And then to put the oval in for the CD, so some customers buy only compact discs, so there's no overlap with the other two events at all. So we have this little oval off to the side on its own, representing the customers who only buy a CD. So that is the end of the video on 3.5, which covered tree diagrams and Venn diagrams.